Hello. We are now classifying the states of a Markov chain, and we last time defined basically the first passage probabilities, and so basically there is this probability Fij of n, and this is the probability that for a homogeneous discrete-time Markov chain that x0 you are in state I, given that you after n steps or at time instant n you are in state j. Okay, if you just have this is the p probability, but to be a first passage probability, then basically we need those extra conditions that x1 is not equal to j, x2 is not equal to j, up to xn minus 1 is not equal to j, which means that this is the transition probability from I to j such that the chain enter into state j for the first time after n steps. So there is basically no visit to j at time instance 1 up to n minus 1. Okay, so this is the F probability, and basically Fij will be a sum of those i's. Remember that by definition we'll take Fij of 0 is equal to 0. I mean, so again, it's up to you. You can start from 0 or 1 depending on convenience. And Fij without any superscript is the sum of those guys. And in terms of the generating function, so remember there is the generating function Fijz, which is summation n from 0 to infinity Fijn z to the power n. So if you put z equals 1, you will get basically a big Fij of 1, and it is also the same as this summation here. This is the probability of starting, given that we start in I, that we will visit j sooner or later. So this is a summation over n. So if we sum over n, we basically say that given that we start in I, we will eventually, sooner or later visit j. So this is when you sum those f's, this is a probability. When you sum the p probabilities, this is not a probability, and we will understand the meaning later in this lecture. Okay, but the f's, when you sum those f's, basically you get a probability, and you get something that is less than or equal to 1. Okay, now if this summation is 1, okay, then the sequence Fij of n becomes a PMF, right? So those guys are non-negative and their summation is 1, and this will be the first passage distribution from state the first passage distribution to state j starting from I. Okay, so again, Fijn, now for n, is 1 or 2 or 3, it becomes a PMF, a proper PMF, if the summation of those guys is equal to 1, which means that if Fij without any superscript is equal to 1, and Fijn will basically be the probability that starting from I, you will enter into j for the first time. It's a first passage probability after n steps. Okay, now Fij may be less than 1. So Fij may be less than 1. So actually, let's write this. So Fij may be less than 1, and if it is less than 1, it means what? What is the meaning that the summation of Fij of n, where n is a natural number, that this summation is strictly less than 1? It means that there is a probability, okay, so there is a probability which is 1 minus Fij that j is never visited given that we start in state I. Okay, so if the sum, so this summation again is something that is less than or equal to 1. If it's 1, it means sooner or later j will be visited. If the summation is strictly less than 1, it is like, so Fij of n is not a proper PMF. right? It's like there is a missing value. The missing value is basically that n is equal to infinity, which means that, this is the way of saying that there is a probability, which is 1 minus Fij, that you start in I, but you never, ever, in any finite number of steps, no matter how large, you visit or you enter into state J for the first time. Okay? Now, before proceeding, I want to highlight something, okay? Which I think is very important, like to solve, for our further understanding here, and to understand things like random walks and to solve homework problems, which is first passage is a stopping time with respect to the sequence x0, x1, x2, and so on. Okay, what is basically the meaning? What is basically the meaning of this? So suppose that you are studying this random variable, which is the number of steps all the time that is needed so that you, given that you start in I, that you enter into state J for the first time. Okay, so suppose Tij is the random variable that given I, J is entered for the first time. Okay, now you ask your question. If you want to check whether something is a stopping time with respect to a sequence, what you need to check is, you have several options. One of them is to check this event. Tij is equal to m. So this event requires knowledge of what members or what elements in the sequence of random variables. So to make the decision that it takes m steps to start from I and then to enter into J for the first time, what do we need to check? Okay, so x0 is equal to I, x1 should not be equal to J, x2 should not be equal to J, xm minus 1 should not be equal to J, and xm should be equal to J, right? So to examine this event, you need knowledge of everything in the sequence up to m, and that's the magic number. So if you study what is what is this event that the stopping time, or here basically the first passage time is m, what do you need to know? Do you need to know every x? No, you just need to know x of 0, x of 1, up to x of m. And basically this event is true if this is true. If x of 0 is I, x of 1 is not j, x of 2 is not j, x of 3 is not j, up to x of m minus 1 not j, but then x of m is j, then this event will be true. Otherwise it is not true. So do we need x of m plus 1? No. X of m plus 2? No. And so on and so forth. So indeed this is a stopping time. So the time that it needs, or the number of steps that it needs to enter into a state from some other state for the first time, the so-called first passage, this is a stopping time with respect to the sequence of random variables. Okay, and so again, what is the benefit of knowing something like this? So previously, knowing that something is a stopping time will allow us to use Wolff's inequality. Now for Markov chains, another thing is the strong Markov property. So the strong Markov property, which means that if you condition on x of t is equal to I, something like this, and t is a stopping time, then basically we still have the Markov property. The future is independent of the past given the present. So despite the fact that the index of x is a random variable, but so long as it is a stopping time, then there is a Markov property, okay, which is called the strong Markov property. And again, this is very useful in solving problems and in dealing with things like random walks and so on. Okay, so keep this in mind. First passage is stopping time. So while we are at it, last visit. So you ask yourself at any instant, when was the last visit to some state from some other state? Is this a stopping time? Is this the last visit? Now the problem with last visit is that to know that it is the last, you need to know the full future, right? So if basically is J lost, or is J visited from I for the last time after m steps, or m is anything of your choice. How do you know that it is the last visit? You need to know the full future, right? If I give you, so if n is 7, after let's say 7 steps, well, if I give you x of 10, and then you see that the chain is not in J in x8, in x8 or 9 or 10, but can you declare that basically the last visit was at time instant 7? No, because perhaps there is a coming visit in the future. So last visit, it's not a stopping time. Not stopping time. Okay. So something like this, you cannot apply Wolf's inequality if needed. You cannot apply a strong Markov property and so on. Okay. So knowing these things is again is very important. So that you can specifically for Markov chains, once you recognize that something is a stopping time, then now it is valid to basically exploit the strong Markov property. Now. Let's go back to our topic here. That now let's talk about JJ. So it's basically we are talking about the first passage from state J to state J, so which means that you start in J and then you go to some other state and then you enter into J for the first time. So again, FJJ, this will be summation JJ of n, and n is a natural number. Okay. And if this is 1, it means that if you start in state J, then sooner or later you will come back to J. Then sooner or later you will come back to J. And if TJJ is the number of transitions required until you go into J again for the first time, then again this is a proper random variable, and the probability that is equal to n is exactly this FJJ of n, which is by definition the probability that you start in J and then you enter into J again for the first time after n steps. So this random variable TJJ is called the recurrence time. The recurrence time, which recurrence means that a repeat, right? So to recur means to happen again. To happen again, what is happening again is state J. Okay, so start in J and then you wonder, you wonder what is the probability of going back to state J for the first time in 1 step, 2 steps, 3 steps, 4 steps, and so on. And so those probabilities are basically FJJ of n. And their summation, do you expect their summation to be exactly 1? It may be 1. Okay, it may be 1, which tells you that state J is guaranteed. So almost surely it will be visited from state J in some finite number of steps. But it can be strictly less than 1, which means that there is a probability that you start in J, but you never ever come back to J. So basically, this TJJ, which is a random variable giving you the number of steps to go from J and then to enter back into J for the first time, this can be a defective random variable. A defective random variable in the sense that it has one of its possible values is infinity, happening with a strictly positive probability. And to say that TJJ is equal to plus infinity, it means that in no finite time whatsoever you will go back into staging. Okay? But if FJJ is equal to 1, then this is a proper PMF, and again, almost surely you will go back to J for the first time, starting from J. And since this is a PMF, you can also like find its mean first moment, and the first moment is called the mean recurrence time. So the mean recurrence time is the expected value of this thing, and so basically it is a summation of n multiplied by the probability. So it's n multiplied by FJJ of n, and we can use we can obtain the probability generating function to obtain moments via differentiation. So it is something like the characteristic function, like the moment generating function, like the Laplace transform. All these things, you know, under some conditions you can use their derivatives to obtain the moment. So basically, you know, this the mean recurrence time can be obtained by from the derivative of, so FJJ of z is this summation, and from 1 to infinity FJJ of n z to the power n. And if you differentiate this guy with respect to z, you know, then you know, I mean, like if you do things non-rigorously, if you differentiate this with respect to z, and you know, assuming that you can interchange the order of differentiation and summation, then basically you will have an n getting downstairs, right? You will have an n getting downstairs, and you will have zn minus 1, and so you can basically multiply by z, so that you get something that looks, you know, something that looks like the definition here of the mean recurrence time. Okay, and now are we allowed like to interchange the order of summation and differentiation? Well, I mean, for those of you who took the signals and systems course, or you know this already for power series from any math course, that basically if you have a power series, and this is indeed a power series, and it has a region of convergence, and here the region of convergence is basically the unit circle in the z plane, as yeah. Then it is basically the power series is infinitely differentiable in the interior of its region of convergence. Okay, it's infinitely differentiable inside its region of convergence, and then you can prove actually that you can indeed interchange the order of differentiation and infinite summation. Okay, so again, if we look back here, if you have this is again, if you know power series, this is a valid statement. Okay, again, it may look fishy because it looks like we are differentiating and we interchange the order. Yes, I mean, this is valid. This is valid. And now, what will happen if you take the limit of this thing as that goes to 1? You know, the limit of this thing as z goes to 1 is exactly the limit of this thing as multiplied by z, right? Because z goes to 1. And so if you multiply this thing by z, z itself goes to 1 outside, so the limit of this thing as z goes to 1 is exactly the limit of this thing multiplied by z as z goes to 1. And now, so when you multiply this thing, so z dfjj of z is basically summation n from 1 to infinity n fjj of n z to the power n. So basically this is like a generating function for the sequence n fjj of n. Then what? So basically Abel's theorem. So this was the last thing in the previous lecture, which tells you that, well, if you're talking about the probability generating function of a sequence, and this sequence is non-negative, and this sequence is non-negative. Remember, basically, if you have a sequence g of n, and g of n is greater than or equal to 0, then here is our sequence. It is n fjj of n. It's a non-negative sequence. So fjj is a probability, and n is a natural number. So if you have a sequence that is non-negative, then you can basically study things in the z domain. And we have this rule that if you take the limit of the generating function, z goes to 1, then if this is equal to L, and L actually is allowed to be equal to plus infinity, then we are sure that basically the summation of g of n, okay, that this summation here is equal to L. So if this limit is infinity, this is infinity. If this limit is a finite number, this is a finite number. But the condition is that actually we are talking about a non-negative sequence. Okay, so Abel limit theorem basically will tell you that if you take this limit here, it is exactly equal to the summation, summation n from 1 to infinity n fjj of n, which by definition is the first moment or the mean recurrence time. Okay, so now a state in which fjj is equal to 1. So if this is true for state j, then again the meaning is that this state, if you start in j, then sooner or later with probability 1 you will come back to j. In some, it may take you 1 trillion years to go back to j, but it will happen sooner or later. Okay, and so if fjj is equal to 1, then our state is given a name. So this is the first class of states. It's called a recurrent state, and some references refer to it as a persistent state. Okay, and here I will basically prefer recurrent. Okay, it's a recurrent state or persistent state. However, recurrent states come with two flavors, depending on what the first moment is. Okay, so basically a current state is its first moment, is it some finite positive number, or it is an infinite, it's plus infinity. If it's a plus infinity, then we say that the state is non-recurrent. And if it is basically, if the first moment is finite, then we say that the state is positive recurrent, and some references say that it is null recurrent, or it is regular recurrent. Okay, so here is basically the definition. So FJJ can be one way of classifying the states of a Markov chain. And again, let's remind ourselves what is the meaning of this thing. It is the probability of FJJ of n from 1 to infinity. You can start from 0 if you wish. And basically, this tells you the probability that you start, given that you start in J, you enter into J for the first time after exactly n steps. Now, we have two possibilities. So the first possibility that this guy is equal to 1, and the second possibility that this guy is strictly less than 1. So if this guy is 1, then we are talking about recurrent state. And if this guy is less than 1, then we are talking about state that is not recurrent, and it has a name. It is called the transient state. Transient. Okay? So we have transient versus recurrent. So if JJ is strictly less than 1, the state is transient. And a transient state in the context of Markov chain, it means that it is a state such that if you start in the state, there is a probability. There is a positive probability, and this probability is exactly 1 minus fjj, that you will never ever come back to the state in any finite number of steps. Now, if fjj is equal to 1, then we are talking about a recurrent state. And now recurrent states, now we have basically the following. So the mean recurrence time is equal to plus infinity, or the mean recurrence time is less than infinity. So in this case, the state is called the positive recurrent, okay? And in that other case, it's called non-recurrent, okay? And so the states in Markov chains are basically those three types of states. So the state can be transient, it can be non-recurrent, or it can be positive recurrent. The state in a discrete time, in a homogeneous discrete time Markov chain, can be transient, with fjj that is strictly less than 1. It can be null-recurrent. So null-recurrent means that fjj is exactly equal to 1, but the first moment of the recurrence time, or the mean recurrence time, is exactly equal to plus infinity. And if fjj is equal to 1 and the mean recurrence time is a finite number, then our state is positive recurrent. Okay. Now, there is a statement that is mentioned here, and it is a mysterious statement, and we do not know yet why this can be true, but keep it in mind that if the number of, basically if the discrete random variables of your Markov chain, if they are finite, they take or they assume a finite number of values. So if the state space is finite, then the discrete time Markov chain is composed of transient and positive recurrent states, and you can never have non-recurrent states. So non-recurrent states do not occur in finite Markov chains. Okay, so this is something. Keep in mind again, we don't still have the tools to make this argument, but keep it in mind. So they may appear in infinite chains. And when I say infinite chains, I mean it's chains in which the state space is countably infinite rather than being finite. If you are talking about a finite chain, then we are talking about either transient, state is transient, or positive recurrent. In the infinite case, you start getting this funny null-recurrent thing. And again, we will gradually develop our understanding of why basically this thing does not appear in the finite case, but it can appear in the infinite case. Let's take an example. So this is a finite Markov chain, and basically this is the TPM. And what is F11 of n? So this is the probability that starting in state 1, so 1, 2, 3, and 1, 2, 3. What is the probability that starting in state 1, you enter into state 1 for the first time after n steps? Okay. So remember that basically Fij1 is exactly equal to Bij, 1 which is equal to Pij. And so here we have 1/3. So the probability that you start in state 1 and then you enter into state 1 after just one step for the first time, this is exactly the transition probability from 1 to 1, which is equal to 1/3. So what is the probability that you will enter from 1 into 1 after exactly 2 steps? So exactly 2 steps, it means the following. Now, can you go from 1 to 3? Can you go from 1 to 3? No, you cannot go from 1 to 3 because you can see here that state 3 is an absorbing state, as we talked about in the previous lecture. State 3 is an absorbing state, so if you do a transition from 1 to 3, you are stuck in 3 forever, and you will never ever get back to 1. And so the hope to go from 1 to 1 in 2 steps and enter into 1 again for the first time is that you make a transition from 1 to 2, and this happens with the probability 1/3, which is this one here, and then in the next time instant, you will basically the Markov chain moves from state 2 to state 1, and this happens with probability 5/6. And so basically F11 of 2 is 5/18. And now what about F11 of 3? Can you start in state 1 and then enter into state 1 again after 3 steps or more? Let's think about it. So you start in 1. If you go to 3, you are stuck in there forever. If you go to 1, then you enter into 1 for the first time after 1 step. And then if you go to 2, you have 2 options depending on this structure of the TPM. If you go into 2, you either go to 3 and you will stop there forever, or you come back to 1. So the first passage event for state 1 is only for small n equals 1 or 2, right? So if you start from 1, you can enter into 1 again for the first time, either after just 1 step, and this is via doing a 1-to-1 transition, or after 2 steps via doing a 1 to 2 and then 2 to 1 transition. Nothing else, right? Because can you enter into 1 for the first time in 3 steps? How can you do it? There is no way you can do it. And so actually F11 of n is equal to 0 if n is greater than or equal to 3. So what is the summation? N from 0 to infinity, F11 of n. So it is just the sum of these 2 numbers, 1/3 and 5/18, which is 11/18, which is less than 1. So state 1 in the given chain is a transient state. That's a transient state. It is transient, okay? And state 2, let's say, what is the probability that you enter into, you start in state 2 and then you enter into state 2 for the first time after 1 step? 0. This probability is 0. Why it's 0? Because in state 2 you either go to 1 or you go to 3. Okay, the probability of self-transition is equal to 0, and so basically you cannot go from 2 to 2 in just 1 step. So what is the probability of going from 2 to 2 into 2 steps? So 2 steps mean the following. So 2 steps means that you start in 2, Okay, and then you don't want to go to 3, it's an absorbing state. So you go from 2 to 1, and then from 1 you go to 2. And so this would be 5 over 6, which is the transition probability from 2 to 1, and then you multiply by 1/3, which is the probability of making a transition from 1 to 2. And so in 2 steps, it's 5 over 18. What about doing this transition in 3 steps, 4, and so on? So basically, if you want to go into a 2 for the first time in n steps, then you start in 2, you make a transition to 1, and then you remain in 1. You remain doing self-transitions in 1, 1 to 1, 1 to 1, 1 to 1. Again, you are prohibited from going to 3 because it's an absorbing state, and you are prohibited from going to 2 because you are focusing on a first passage probability, right? So you do those transitions from 1 to 1 for n minus 2 times, and then you go back to basically from 1 to 2, right? So basically, this event here is like you go from 2 to 1, okay, and then you keep 1, 1, 1, okay, with the number of steps that matches the n here, and then you go back to 2. Okay, and so this looks like a geometric. The f to 2 of n is like a geometric, basically random variable, but it is not really geometric. It is not really a proper random variable. If you sum, you will find that the summation is equal to 5 over 12, which is less than 1, indicating that also state 2 is a transient state. Okay. Now, state 3. State 3, what is basically F33 of 1. F33 of 1. So if you enter into 3, or you start in 3, what is the probability of going back into 3 for the first time after 1 step? That's 1. So actually, for the third state, F331 is equal to 1, and the other Fs are equal to 0. So the summation, F33, which is summation n from 0 to infinity, F33 of n is equal to 1, but it is 1, okay? And so that's a recurrent state. And it is specifically a positive recurrent state, okay? So basically think about it. What is the mean recurrence time? On average, how many steps do you need if you start in 3 that you come back to 3? Well, 1 step, right? Because 3 is an absorbing state. So if you start in it, then with probability 1, you go back to 3 in just 1 step. And so basically the mean recurrence time is exactly equal to 1, which is less than infinity. So state 3 is positive recurrent. Okay, so if we want to do the classification for our simple Markov chain, states 1 and 2 are transient, and state 3 is positive recurrent. Any questions? Okay. When we talk about the states of a Markov chain, then we also characterize something called the period. So there are states that are called periodic, and there are states that are called aperiodic states. And so let's define this. And state J is a periodic with a period, and the period, if the state is periodic, then its period by definition is strictly greater than 1. So the period can be 2 or 3 or 4 or something like this. Okay, and the state is periodic. Basically, if starting from the state, you can be back at the state again at only at the integer multiples of this big T. So suppose that big T is equal to 2, right? So we say that the state is periodic with a period 2 if starting from that state, you can possibly be in that state again only at time instance 2, 4, 6, 8, and so on. Okay? So basically this is the definition of a periodic state with a period. Okay, so specifically we focus on the set n such that bjj of n is greater than 0. So basically, what is this set? This is the set of time instants at which the discrete time Markov chain can possibly be in state J. So that's the set. Now, what you do is that, so so there are all values of n for which you can, at those values, at those time instants, you can be in state J with a strictly positive probability. Now, if you take the GCD of those guys, okay, the GCD of those guys, this is the definition of the period of the state, so long as the GCD is strictly greater than 1. Okay, so like in signals and systems, we actually allow a period to be equal to 1, but again, for discrete time Markov chains, the period must be 2 or more, and the period is equal to big T if where T is greater than 1, if the chain starting from state J, it can be in state J, it can be, which means with a positive probability at time instance T, 2T, 3T, and so on. But otherwise we are sure that the chain cannot be in state J. So if your state is not periodic, so basically if you complete this GCD and it is not a number that is greater than 1, in fact it is equal to 1, then our state is aperiodic, which means again that the GCD of this set here is equal to 1. A state that is aperiodic and is positive recurrent, so it means that it is recurrent and the mean recurrence time is a finite number. So if it is positive recurrent and also it is aperiodic, it has a name, it's called an ergodic state. So if you hear the term, this state is an ergodic state, it means this combination. It is a positive recurrent state that is aperiodic. It is a positive recurrent state that is aperiodic. And aperiodicity, again, it means that you go and compute this Pjj of n. Okay, so this thing here is the probability that xn is equal to j, given that x is equal to j. You compute all time instants for which this thing is strictly positive, and then you compute the GCD. If you end up with the GCD being equal to 1, then your state is aperiodic. And if it's aperiodic and the state is positive recurrent, so positive recurrent, remember that this thing means that Fjj is equal to 1 and mu jj is strictly less than infinity, then the state is called an ergodic state. Now, let's take this Markov chain from 1 to 2 with probability 1, from 2 to 1 with probability 1. Now, what is B11 of n? So if you start in state 1 at time instant 0, then at time instant 1, you are sure that you are not in state 1. Because with probability 1, you will make a transition to state 2. Then you are sure at time instant 2 that you will be back in state 1, and so on and so forth. So basically, for both states, actually, they are periodic states with a period that is equal to 2. Both states are period with a period that is equal to 2. And again, like if you start from a state, what is the probability of entering into the state for the first time after n steps? So you'll find that for a general n, this probability is equal to 0, except when n is equal to 2, right? Because from each, so from 1, how many steps you are guaranteed to enter back into 1 after 2 steps? You start in 1, you make a transition from 1 to 2, and then another transition from 2 to 1. So with probability 1, you will go back into state 1, starting from 1 in 2 steps. So basically, f11 of n and f22 of n are equal to 1 for n that's equal to 2, 0 otherwise. But the idea is that if you sum the f probabilities, one of them is equal to 1, the others are equal to 0, so the summation is equal to 1. So both the states are recurrent. Okay, so both the states are recurrent states. Okay, so here what we have is the states are both recurrent. And what is the mean recurrence time? How many steps on average do you need to go back from 1 to 1 or from 2 to 2 for the first time? 2. Right? So basically, mu 1 1 is 2 and mu 2 2 is 2. Right? 2 steps. Because again, like to enter from a state 1 or 2 from itself, after for the first time, it only happens with probability 1 after 2 steps. And the mean recurrence time is 2, which is a finite number. And so basically in the Markov chain that you see in front of you here, both states are basically positive recurrent, but those states are not ergodic because actually they are positive recurrent and they are periodic, and the period is exactly equal to 2. Okay, so again we can classify the states based on FJJ. Or we can classify the states based on whether they are periodic or aperiodic. Now, can we do the classification related to the B probabilities, the transition probabilities, not the first passage probabilities? Okay. So let's see. Now, let's look at this summation. So summation n from 0 to infinity bjj of n. Now, this summation here, okay, by upper limit theorem, basically we are talking here about probabilities, so they are non-negative. So by upper limit theorem, it tells you that you can do your stuff in the z domain. So if you take bjj of z and take the limit as z goes to 1, then basically you either get a plus infinity or a finite number, and in both cases, this summation will be equal to that limit. So from the previous lecture, remember the relationships between, so we have this relationship that Pij. So if I is not equal to j, Pij is equal to f. Well, let's put it. Bij of z is Fij of z, Bjj of z, and then Pii of z is equal to 1 over 1 minus Fii of z. Okay, so we have these two relations from the previous lecture. And so here we are talking about Jj. So Bjj of z is 1 over Fjj of z. And then if you take the limit, well, the limit will be 1 minus Fjj. So again, using upper limit theorem, it turns out that, so we did the classification of states based on Fjj, whether it is less than 1, and hence we have a transient state, or it is exactly equal to 1, and hence we have a recurrent state. Now, what we are saying is that basically this quantity here is very much related to this summation, right? So summation n from 0 to infinity bjj of n by upper limit theorem, this is exactly equal to 1 over 1 minus Fjj. So if your state is recurrent, then this guy is equal to 1, and then we have 1 over 0, which is plus infinity, and so basically the summation is equal to plus infinity. So another way of describing a recurrent state is to say that for a recurrent state, if you do the summation of bjj of n from 1 or from 0 to infinity, okay, from 0 to infinity, okay, that this will be an infinite number. Okay, so this is another way of understanding a recurrent state. Again, this is equivalent, so this is if and only if Fjj is equal to 1. Now, if we are talking about a state I is not equal to j, then we have this other formula for the relationship between the b and f probabilities. Pij of z is equal to Fij of z, Bjj of z. Now, what is the summation of Bij? Okay, again, probabilities. So by upper limit theorem, the version in which basically we are summing stuff that is non-negative, then we can actually study the generating function and take its limit as z goes to 1. And this limit will be the limit of this product. And then we have two terms. And now suppose that basically this guy is not equal to 0. So this guy here, the limit is Fij, which is the probability that sooner or later you will go into J, you will enter into J for the first time starting from state I. If Fij is not equal to 0, it's just some positive number, then basically it is multiplied by a limit. And if your state J is a recurrent state, then this limit here is basically the sum of so this limit here will be the summation bjj of n from 0 to infinity, and this will be equal to infinity, and so infinity multiplied by a positive number will be infinity. Okay, so this is like sort of like something. Now we are relating states together, and this is extremely important. It turns out that basically when we classify the states, that if we are able to reach a state from another state, then basically if we are able to go from some state to some other state, then this is important in making basically in classifying both the states. Okay, so this is like the first observation. So J is recurrent. J itself is recurrent, right? And so this means that fjj is equal to 1, and summation bjj of n from 0 to infinity is equal to plus infinity. Okay, so we can say this, we can say that. Now let's say that fij, so I is some other state, fij is strictly positive, which means that from I, J can be reached sooner. So fij is equal to can be okay. So if fij is strictly greater than 0, then this means that you know you have a positive probability of going from I to J. Okay, so J can be reached sooner or later with a positive probability. So in that case, and using the relationship between the probability generating function of the P probabilities and the F probabilities, we show that basically summation n from 0 to infinity, Pij of n, that this guy also will equal to plus infinity. Okay, now let's go back to our relationship here. Now we consider the case in which fjj is 1 over 1 minus 1 is basically infinity. But what if j is a transient state? If j is a transient state, then fjj is strictly less than 1, and so basically this summation here will be a finite number. Okay, so for a transient state, fjj is less than 1, this summation will be a finite number, and you can also show that basically the summation of bij of n is a finite number. Now, if you have a summation like this or that that is finite, then we know from the rules that basically the nth term should converge or should tend to 0 as n goes to infinity. Okay, so if those guys are convergent, then limit n goes to infinity of fjj of n is 0, and limit n goes to infinity bij of n is equal to 0. So here there is a claim. If you have a finite discrete time Markov chain, so I made a statement that till now is like a mysterious statement, which is that in if the Markov chain is finite, then you can never have a state that is null-recurrent. Okay, but the states can be transient. Or they can be, positive recurrent. Okay. Now I will make another claim, but this one we can understand given what we know till this point. So if you have a finite Markov chain, then it cannot be the case that all states are transient at the same time, which means that if you have a finite discrete time Markov chain, at least one of your states must be positive recurrent. So we can have a mix between positive recurrent and transient states. We can have that all states are positive recurrent, but it is not feasible mathematically to have all states to be transient. Okay, so let's see what is this story. We have again a finite state discrete time Markov chain. Okay, so for a discrete time Markov chain in which all the states, so if all the states are transient, then limit n goes to infinity, bij of n is equal to 0, even for I not equal to 0, even for I equal to G. What are those guys? So remember, basically that the element, this is an element of p to the power n, the transition probability matrix raised to the power n. And so now what we are saying is so let's assume, so we are doing something by way of contradiction. Let's assume that we can really have a finite discrete time Markov chain in which all the states are transient. Then according to the rules till now, it must be the case that if you take the transition probability matrix and raise it to higher and higher powers, then the elements of p to the power n must decay. All of them must decay to 0. All of them must tend to 0 as n goes to infinity. But this is problematic because a transition probability matrix raised to any power is a Markov matrix or a stochastic matrix in which the sum of each row is equal to 1. So there is a contradiction here. The contradiction is that you are saying that every element inside the matrix will tend to 0, but at the same time, for every natural number small n, p to the power n has the property that the sum of the elements in a row, basically this summation is equal to 1. Okay, so this is given, and I think like you have a problem in the current homework to show that a Markov matrix multiplied by a Markov matrix. So Markov matrices are matrices that with non-negative elements, and the sum of each row is equal to 1. Multiplying a Markov matrix by another Markov matrix will yield a Markov matrix, and so taking a Markov matrix and raising it to any power will be a Markov matrix. And this is actually from even by definition, basically that since p to the power n still gives you the transition probabilities in n steps, then it must be the case that each row basically sums to unity. So the sum is equal to 1. Now take the limit of both sides. Take the limit of both sides as n goes to infinity. Now the limit of 1 is 1. And now if the state space is finite, then we have a finite number of terms in this sum. And the limit operation is a linear operation. So basically, if you have a finite number of terms in a summation, then the limit of the sum is the sum of limits. This is not generally true if we have an infinite sum. But our assumption here is that we are talking about a finite discrete time Markov chain. So we are allowed to take the limit inside. But if we take the limit inside and evaluate the limit, then the limit is 0 for every entry in the matrix under the assumption that every state is a transient state. And so the limit is 0, and the sum of zeros is 0. And so now we basically have the conclusion that 1 is equal to 0, which does not make sense. So our assumption is wrong. And it cannot be the case that you have a finite discrete time Markov chain in which all the states are transient. So you need at least one positive recurrent state. So in general, you have a mixture of positive recurrent states and transient states, or perhaps all the states are positive recurrent. But in a finite discrete time Markov chain, it cannot be the case that all states are transient And again, I will say it without justification now, you cannot have even one state or more that are null-recurrent. Null-recurrent is a class that will appear only in infinite discrete-time Markov chains. Okay. Now, suppose that you have an aperiodic recurrent state. An aperiodic recurrent state. Then there is something called the discrete renewal theorem or the discrete renewal equation that tells you that if you have an aperiodic recurrent state, then the limit bjj of n as n goes to infinity, you can show that it is equal to 1 over mu jj. And so the proof of this thing I will skip. It's proof, there is a reference to the proof on Blackboard. And the proof is like sort of an exercise in real analysis. It's a tough exercise in real analysis. Okay, so it uses like the concepts of limb soup and so on. This is like I will try to justify many things here, but for this one I will just take it for granted. Okay, so we will take it for granted that again limit n goes to infinity, bjj of n. Again, it's not, this is, this limit is equal to 0 if we are talking about transient states. But now we are talking about recurrent states and specifically about aperiodic recurrent states. And so this limit here is equal to 1 over mu jj, where mu jj is the mean recurrence time. And this is true for non-recurrent states and the positive recurrent states. It's just the case that if the state is positive recurrent, this will be a finite number and you will get something 1 over mu jj will be a finite positive number. But if the state is non-recurrent, then mu jj is plus infinity and 1 over plus infinity we will take it to be 0. Okay, and so this again we will take for granted. But if you are interested, you can read the proof. Starting from this, let's study something like, okay, let's study this limit here. Limit n goes to infinity bij of n. Now, what is bij of n? So bij of n, remember this relationship between the p and f probabilities. It is summation alpha from 1 to n, and then we have fij. So you want to go from I to j in n steps. So you can go from I to j and enter into j for the first time after alpha steps, and then you basically do a transition from j to j in n minus alpha steps. Okay, and so this is like again the fundamental relation between the f and p probabilities, and then you can rewrite basically this summation here. You can have an indicator with alpha less than or equal to n, and then you can extend this summation to infinity. And now we are interested in the limit of this summation. And then now you have an infinite summation, so it is not always valid to interchange the order of limit and infinite sum. But let's investigate the summation of this quantity here. Now, if you look at this quantity here, if you look at the magnitude, basically everything actually is non-negative. Indicator function is upper bounded by 1. The probability is upper bounded by 1. And then you have, so you can upper bound this product by fij of alpha, and the summation of fij of alpha is a number that is less than or equal to 1, which is a finite number. And so since we can take this summand, okay, so the summand is bounded by fij of alpha, which is summable. Okay, which is summable, and so by the dominated convergence theorem, one version of the dominated convergence theorem tells us that we can take this limit inside, and so we can take the limit inside. And if we take the limit inside, then there are two things. So the indicator, this is the indicator that n is greater than or equal to alpha. So now you are fixing an alpha and then taking the limit. So if you fix an alpha and you take the limit as n goes to infinity, sooner or later, basically this n will get very, very large and will exceed alpha. And so the limit of the indicator function is equal to 1. And for basically this quantity here, this is what we will take for granted. This is 1 over mu gg. And so the limit of this thing is 1 over mu jj, which can be taken outside the summation, and then you are left with the summation of the Fij of alpha, and this summation is Fij. Okay, so now we have this very important result that limit n goes to infinity, Bij of n is, so here j, okay, so Bij of n, and again here we have j is aperiodic and recurrent. So this limit here is Fij over mu jj. So mu jj is the mean recurrence time, mean recurrence time of state j. So this means that this is the time, you know, that you need on average starting from j to go back to j for the first time. And so this is mu jj. And in the numerator we have Fij, and Fij is the summation n from 1 to infinity Fij of n. And this is the probability that sooner or later you will go from I to j and enter into j for the first time. And this quantity, it can be 1, meaning that with probability 1 you will visit j from I, or it can be less than 1, which means that there is a probability that starting from I you will never ever visit state j in any finite number of steps. Okay, so again this limit statement is very important. Now remember, when doing state classification, we use this relationship here, that summation n from 1 to infinity Bjj of n is equal to 1 over 1 minus Fjj. And so for recurrent states, this will be 1, and this summation will be infinity. For transient states, this will be less than 1, and this will be finite. But actually, what is the meaning of this thing? What does it mean that you take the B probabilities and you just sum them? Is there a meaning? And yes, there is a meaning. Okay, and the trick here is basically to take this probability. You know, here I will do it for a Pij, or generally speaking. And so, what is this probability? Let's write it using its definition. It's the probability that xn is equal to j, given that x0 is equal to I. And rather than having a probability, I can write this probability as the expectation of an indicator that tells you that xn is equal to j, given that x0 is equal to I. Right? So basically, you can write this probability or the expectation of, so the indicator is like, you know, a Bernoulli random variable, and the probability that xn is equal to j, given that x0 is equal to I, is the expectation that given that x0 is equal to I, you know, we have the expectation of indicator xn is equal to j. Now, we are talking about non-negative stuff. Non-negative stuff, it means that I can take actually this expectation and I can put it outside. And now what we have is that the summation of the Pij of n is an expectation of a sum of indicators. What is this? So here we are saying that we start in I, and the sum is the number of visits to j, starting from I. So basically, this summation here is, it has a meaning. It's the mean number or average number of visits to j starting from I. Okay, and so it has a meaning. And if you put I equal to j, then basically it is, you know, you can start in j and ask yourself, if you start in j, how many times on average you will visit state j again. So basically this summation of the P probabilities is related to the expected number of visits. Okay, and what if I stop the summation? Okay, so what if I take this summation here, summation n from 1 to m, Bij of n? So what will be the meaning of this thing? It will be a summation as such, but you stop at m. So this will be the mean number of visits from I to j in m steps. So if you go to infinity, you basically you study basically the average number of visits over basically an infinite time horizon. But if you stop at some time instant m, then you are basically saying, okay, how many visits that will occur during the first m steps. Okay, so the mean number of visits from I to j in m steps, or during the first m time instance. Okay, so again, the summation of the p probabilities, and like I think starting from the I don't remember about the problems in homework 11, but in homework 12, there will be like this visiting, how many number you visit, and you can actually approach the visiting problems in a number of ways. This is one of them. So one of them is, again, that the summation of the p probabilities, if you sum over m time instance, then it is the number of visits during the first m time instance. If you go to infinity, then it's just the mean number of visits, taking all time into account. It is related to the mean number of visits. Okay, so it is an important concept. So it has like sort of a meaning, and it has a meaning like in classifying the states. If it's this summation for bjj of n, if it's infinity, we are talking about a recurrent state, and if it is finite, then we are talking about the transient state. So here is basically a summary that is very important. So if our state is transient, fjj is less than 1, but for null-recurrent and positive-recurrent states, fjj is equal to 1. And then this summation bjj of n, which is the mean number of visits to j starting from j over the time horizon, then this summation here is finite for transient states. So for transient states, by their name is transient. So it means that the number of visits, the average number of visits, is a finite number, which means that there will be an instant of time after which you will never come back to state j if state j is transient. But if state j is recurrent, then this summation is equal to infinity. What about this limit here? The limit is 0 for transient and non-recurrent states, and 1 over mu jj for positive recurrent states. And this is if the states are aperiodic. If the states are periodic, then actually the limit of this sequence does not exist. You need to take the sequence in which you study the time instance n multiplied by the period. So here d is the period. And in that case, the limit is the period divided by mu j. Any questions? Okay, so state j is reachable or accessible from state I if there exists an n greater than or equal to 1 such that bij of n is greater than 0. Okay, so if bij of n for some n is greater than 0, then starting in I, there is some possibility, some positive probability that you will be in state j. Now, so here in this case, if this is true, then j is accessible from I. Now, if I is accessible from j and j is accessible from I, okay, then we say that states I and j communicate, and this is denoted that I. So you can go from I to j or j to I. Okay, so I goes to j. Okay, it means that basically there exists m. There exists m that Pij of m is strictly positive. There exists L such that Pij of L is strictly positive. So sorry, Ji. So Gi. So which means again that starting in I, there exists some m steps, and in that case it's not like we do not say that this probability is exactly 1. We say it's just positive. So there is some positive probability that in n steps, starting from I you will be in j, and after n steps, if you start in j, that you will be in I. Again, you need just a positive probability. So if j is accessible from I, and if I is accessible from j, then we say that the two states communicate which means that they are reachable or they are accessible from one another. Okay, that's just a definition. Now, let's study this very important case in which a state J is reachable from state I, and state I is specifically a recurrent state. So I and J is reachable from I. Okay, so so there exists an M such that Pij of M is greater than 0. So J is reachable from I, but now we have this little piece of information that I actually is recurrent. That I is recurrent. What can we say? What should we conclude? So the first conclusion is that if this is true, if I know that J is accessible from I, and if I is recurrent, then it must be the case that I itself is reachable from J. So as a conclusion, it must be the case that you can go from J to I. Okay? And the reason for this is that if you go from I to J, and going from J to I happens with probability 0, then if you are in state I, with non-zero probability, you will go to J. But then, if I is not accessible from J, then with a non-zero probability, you will go from I to J, and then from J you will never go back to I. But this contradicts the very concept that I is a recurrent state. A recurrent state always always appears in the sequence x1, x2, x3, and so on. That's the meaning of a recurrent state. It never appears, it never disappears. Being recurrent, it means that it will appear again and again and again and again. It appears infinitely often. So if I is recurrent and J is accessible from I, suppose that, so by way of contradiction, suppose that actually I is not reachable from J. Then with a positive probability, you will go from I to J, and then you will never come back to I. But this contradicts the fact that I is recurrent. Okay, so this is like sort of the informal reasoning that it must be the case that I is accessible from J. More formally, if J is reachable from I, there exists M such that Pij of M is greater than 0. Now, there exists an M that Pij of M is greater than 0. Let's talk about the least such M. Okay, so I am talking about an M such that Pij of M is greater than 0. You start in I, you are able to go to J, and basically because it's the least M, then basically at no time step you are back in I, because if one of those is equal to I, then you can go from I to J in a less number of steps. Okay, so I will define, if you go from I to J, there exists Bij of M that is greater than 0, right? But actually M can have many, perhaps an infinite number of values. Just take the minimum of them. Okay, and then there is this inequality, which is generally true. It tells you the following: 1 minus FII. So what is 1 minus FII? FII is summation FII of M. It is the probability that sooner or later you will go from I to I. 1 minus FII is the probability that you start in I, you never come back to I. So this event of starting in I and never coming back to I, it has a probability that is lower bounded by going from I to J in m steps. Going from I to J in m steps. And then from J, you never ever come back to I, 1 minus fgi. And so this is a general inequality. To never come back to I, this can happen by going from I to J or I to K or I to V. I mean, you should have like some sort of a law of total probability and some over all possible transitions from I. So we will just focus on going from I to J. So that's the reason I have here, it's greater than or equal to going from I to J, okay, and then from J, you never come back to I in any finite number of steps. So this is never, so basically this inequality is a general inequality. Now, Fii is 1. So now let's apply this inequality for the case in which state I is a recurrent state. So if state I is a recurrent state, then Fii is equal to 1. And if Fii is equal to 1, it means that 1 minus Fii is 0. And so you have something that is less than 0. And so basically, the right-hand side will exactly be equal to 0. So the right-hand side is a product of two things. One of them, by definition, is strictly positive because we assumed that state J is accessible from I, and then it must be the case that the other term is equal to 0, and so it must be the case that Fji is equal to 1. Again, what did we prove here? If I is recurrent and J is accessible from I, which means there exists some time instant such that I can make a transition to J in that time instant with a probability that is strictly positive, not necessarily equal to 1. If I is recurrent, it must be the case now that J must go to I. Okay, I itself must be accessible from J, and so our conclusion is that it must be the case that both states communicate. And actually, our proof is that Fgi is equal to 1, which means that in state J, sooner or later, you will enter back into state I for the first time with probability 1. Okay, so that's a very nice conclusion. So you start by reachability in one direction. You say that just J is reachable from I, but once you have this condition that I is recurrent, you have reachability both ways. Now I and J communicate, and Fji is 1, guaranteed to be 1. But actually, there is more to say. State J is recurrent. So that's another conclusion. State J is recurrent. It's guaranteed to be a recurrent and not a transient state. Okay? How can we prove something like this? Okay, so J reachable from I. So there is an M such that Bij of M is strictly positive. Now I is recurrent, and we have proved that I itself is reachable from J, and so there exists an L such that Bji of L is positive. And I will call Bij of M alpha, and Bji of L I will call it beta. Alpha and beta are strictly positive. Now let's apply the Shadman-Kolmogorov equations. What is Pii of n plus m plus l? Again, M and L are those guys here. So this is a summation over K in S, and this is PIK in M steps, and then BKI in N plus L steps. And every term here in this summation is non-negative, and so this summation is lower bounded by one term, and I will take the term in which K is set to J. And so this is greater than or equal to Bij of M, Bji of N plus L, and this one is what we call the alpha, which is a strictly positive. And then what we will do is that we will apply Chapman-Kolmogorov again, saying that this Bj, so we have alpha, and this Bji of L is summation K in S, Bjk of N, Bki of L. So you go J to I in N plus L steps, you go from J to K in N steps, and then from K to I in L steps. Now again, this is a sum of non-negative terms, so it is lower bounded by one of the terms, and one of the terms is Bjj of N, so I will choose K to be equal to J, and this will be the lower bound, the summation Bji of L, and Bji of L is what I called beta. And so now we have this very nice equality that Bii of N plus M plus L is greater than or equal to alpha beta, which is a positive number, Bjj of N. Okay? But now you can redo starting from Bjj. So you just switch the roles of I and J. You can do this, and you will reach another equality that Bjj of N plus M plus L is greater than or equal to alpha beta, Bii of N. And so what we have here is these two inequalities. Okay, so this is an application of the Chapman-Kolmogorov equations, okay, and using the fact that I is reachable from J and J is reachable from I, and so we have those two strictly positive probabilities, alpha and beta. Now what is interesting in front of you is that we can take a quantity like Bjj of N, and we can lower and upper bound it by quantity Bii of some other time index, but it's Bii, and vice versa. You may say, then what? Those are just, upper and lower bounds. Then what? Okay. What conclusions can we make right now? Okay, what are the conclusions? Now, let's just zoom. The screen is black. You are sharing. Can you see this screen here? So should I stop sharing and then reshare again? Okay, let's do it. So okay, so let's zoom in this part. So it's now clear, right? So I will assume that it is. So you can see my screen? No, still no. I mean, what happened? Can you see my screen?
Yes, it's okay now. Thank you.
Okay. 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 So BGG of n, so let's focus on this part here. Again, so basically, again, we use Chapman-Kolmogorov to basically have those inequalities which may seem like pointless, but actually they are very useful. Now, this is a probability BGG, and it is upper bounded by BIR. Let's sum both sides from n plus L to infinity. Okay, we can do so. Again, I can, so this is true. This is true for every time index n. So you can sum n plus L to infinity, BGG of n, and it's less than 1 over alpha beta summation PII, and again n plus L to infinity, BII of n plus m plus L. Now suppose that J is a recurrent state. If J is a recurrent state, then it means that the summation 1 to infinity of BGG of n is plus infinity. And if this summation is plus infinity, then if you start from any index, any finite index, to infinity, you also get infinity. So this will be infinity. But this is a lower bound on this other summation. And so this other summation is guaranteed to be infinity. So the summation of BII of n is infinity. So it means that state I is also a recurrent state. Again, the argument now is that if you have this inequality, sum both sides from n plus L to infinity. From n plus L, so that basically you don't have a negative index here. But not a problem, okay? If J is recurrent, then basically the sum from 1 to infinity is infinity. The sum from any finite number to infinity is infinity. It's lower bound on the sum of BII. So this summation here from some number to infinity is infinity. So the sum, if you start from 1, is infinity, which means that I is recurrent. And vice versa. Why vice versa? Because you have this situation here. So if basically state I is recurrent, you can also make the conclusion that state J is recurrent. So if states I and J communicate, if they communicate and one of them is recurrent, then the other is guaranteed to be recurrent. Now we can basically use this, the other side. So what if you have this part here? Now if you do the summation, now suppose that J is a transient state. Suppose that J is transient. J is transient. Now if J is transient, and you sum, then this summation will be finite. And this summation is an upper bound on the summation of I. So this summation will be finite and I will be transient. But also this, if I is transient, and again you do summation, okay, if this sum is finite, then the other sum with respect to J will be finite. So what is the conclusion now? The conclusion is that if I and J communicates, J is reachable from I and I is reachable from J. There is a strictly positive probability that you can, after some number of steps, go from I to J or from J to I. In that case, again, using the Chapman-Kolmogorov inequalities and the existence of those two positive probabilities, alpha and beta, you can show that if I and J communicate, then both are recurrent, or both are transient. Both are recurrent, or both are transient. So communicating states, they appear to share the same type. And in the next lecture, we will talk about, so if both are recurrent, I mean, can it be the case that one is positive recurrent and the other is not recurrent? And the answer to this is no. Actually, they have the, if one is not recurrent, the other is not recurrent. If one is positive recurrent, the other is positive recurrent. And even if we talk about periodicity, if one is periodic, the other is periodic with the exact same period.